Rates of chemical reactions can be predicted using rate laws. An equation that relates the reaction rate to the concentration of the reactants is what a formal definition of the rate law is. Rate laws have two components to them. They have what's known as a rate constant, which we represent with a lowercase k, and it's important to note that that lowercase k needs to be distinguished from a capital K, because in the next couple of chapters we'll see that a capital K means an equilibrium constant, and we don't want to confuse the two constants. The other variable we have to take into account in a rate law is the concentration of the reactants. Now, a general form of a rate law looks something like this, that the rate of a reaction equals the rate constant K, reactant A raised to some power times reactant B raised to some power. And all rate laws must be determined experimentally. There is no way you can look at a balanced chemical equation and just know what the rate law is. It must be teased out through a lot of experimentation and backed up by reaction mechanisms. So it's not a trivial thing to identify what a rate law is. One thing that rate laws are is they are always written in terms of concentrations or pressures of the reactants and only the reactants. We don't worry about the products in terms of a rate law. We're only interested in the reactant molecules when we describe the rate of a reaction. Each exponent refers to a reaction order of a particular reactant. That is, in this case, X refers to the reaction order of molecule A, and Y refers to the reaction order of molecule B. The overall reaction order is simply the sum of the exponents. The rate constant, K, is a constant value that does not change unless you increase or decrease the concentration. Depending upon what the exponents are in the rate law, K will have different sets of units. So don't think that all rate constants will always have the same unit. You must take into account what the overall reaction order is. The exponents in a rate law can have any value that's real. They can be positive integers, they can be negative integers, they can be fractional. The only requirement is that it must be a reactant molecule that is being used to describe the rate in the rate law. So in this particular example, we've got a rate of reaction equal to the rate constant K times the concentration of trichloromethane multiplied by the chlorine concentration raised to the power of 1/2. So the reaction order for trichloromethane would be 1, the chlorine reaction order would be 1/2, and the overall reaction order would be 3/2 or 1.5. Now, from these rate laws, we can eventually develop what's known as the integrated rate laws. And we're going to talk about 3 types of integrated rate laws. There's the zero-order rate law, which is somewhat unique in that the rate of the reaction is constant as a function of time. We have the first-order rate law, where the rate of the reaction is dependent upon the concentration of a single reactant. And then we have a second-order rate law, which is either dependent upon the concentration of one reactant or 2 reactants, each raised to the power of 1. So with one reactant, it would be something like the concentration of A squared, or in the case of 2 reactants, it would be A to the first times B to the first. So the general form of a zero-order rate law is such that the concentration at any given instant, A sub t, is equal to the initial concentration, A sub O, minus the rate constant K times the amount of time that's elapsed. If you were to think about this as a graph, this would just be a straight line. The integrated rate law for the first order reaction is equal to the natural log of the concentration at any given time divided by the initial concentration, which should equal the negative rate constant times the time that's elapsed. Or perhaps a more straightforward way of presenting the integrated rate law is simply by saying that the natural log of the concentration at time t is equal to the negative rate constant k times the amount of time that's elapsed plus the initial concentration. Writing it in this form also would produce a straight line if we were to graph the concentration in its natural log form. In both the zero order and first order form of the line, the rate constant k would also be equal to the slope. As seen here, we have two plots. The plot on the left is just the natural pressure of a reaction as a function of time. But you see, when we take the natural log of those pressures and plot it on the graph on the right, we yield a straight line. Well, the slope of that line is the rate constant on graph B. So this is one way we can identify rate constants experimentally. Finally, we have a second order reaction. And for a single reactant dependent second order reaction, we write the rate law as 1 over the concentration of time is equal to the rate constant k times the time plus 1 over the initial concentration. This is a little bit different from the other two in that the rate constant has a positive slope to it. That is, there's no minus kt, this is plus kt. And so what we would find is that a straight line, when graphed, would occur when you plot 1 over concentration as a function of time, with time being on the x-axis. So let's take a look at some data. Here I've got the decomposition of nitrogen dioxide into nitrogen monoxide and oxygen. And what I've done is I've plotted the concentration as a function of time. And what you might be tempted to do is look at it and go, well, that's pretty linear. If I draw a line through it, I certainly see I get a line, but it doesn't quite hit all the points. When this is the case, what we want to do is we want to continue exploring our possible rate laws to make sure that this would indeed be the correct one and not be led astray. After all, while we can get a plot that tells us that pirates and global warming are connected to each other, we shouldn't just rely on this one plot to make that ultimate decision. We need to take into account all possibilities. So, plotting the natural log as a function of time, in this graph right here, we see again, well, the line hits a couple of points, but it doesn't do the best job. If we plot, however, 1 over the concentration of time, we find we get a straight line. And so, with the line hitting all the points, we would use this as the deciding factor to say that this reaction is a second order reaction.